All right. Hello, everyone. I'm Klaas Kelchtermans. I'm a postdoc of Professor Tuitelaars, and I'm just going to give you an update on what we've been doing for the OmniDrone project. So we've been focusing on upcoming real-world demonstrations. So we're busy with applying machine learning for the autonomous UAV navigation task, and we've been aiming at several real-world demonstrations. First one is a simple line following network. So it's a neural network that has the task of following the clearest line above any background based on camera images. So the challenge here basically is to discriminate the foreground from the background. So you have to generalize over many different backgrounds. Why is it relevant? It sounds maybe a little bit, not necessary. Well, the cool thing is that if you, for instance, want to apply a navigation task based on gates where it needs to fly through or where it needs to find a target, often you know the object it's aiming at. So you know the foreground, but you don't know the background. So you want your vision algorithm to be able to generalize for any background. Okay, we've been splitting up this task into two parts. First part is the line segmentation, so where you go from an image to a binary mask, and then the second task is doing the pose and velocity control based on this binary mask. The advantage of splitting it up is that you can train one task on simulated data on data sets, and then the second part of the task is that you can more train interactively and with various methods. So we disentangle them both. Okay. Currently, what's the progress so far? I started with generating a big data set of lines in simulation where a drone automatically flies over a line, and the line is also randomly generated. And I clip these images into binary maps, and then I combine them with a general background, a general texture background, and that gives a supervised data set where you have in the middle images with lines, and then in the bottom you see the binary maps it should detect. And that's for training data, and then the test data is the actual, the real images that I recorded with a drone while flying over the line. Okay, after some iterations of architectures, it appeared to be a more challenging task than I expected. But as you can see on the left, the black and white lines, they represent, do I have a pointer? Yeah. So here you can see the predictions of the network, and here you can see the targets, and you see they are very similar. But then if you go to the test data, there are no lines visible. But anyway, we're already, if in the first step, happy to have this. What we needed to do was to work with deep supervision, where you apply gradients so that the training is done at each intermediate layer, and you combine each intermediate layer in your final output, and then some loss tweaking. Okay. Then if we wanted to know why the line network, this line segmentation didn't work on real data, we had several options. The first option was, okay, it's the background. Probably this texture data set is different. So therefore I recorded some real backgrounds, put a line on top of it, and it could still segment it, as you can see here in the first row. So it wasn't that. Then maybe it's a shape. It learned the line function. So I took a different shape, a square, and it could still detect it. And then maybe it's the foreground. So maybe it's the texture that I used to generate the images. No, it had no issue with detecting these parts. But if I applied some smoothing to the edge of the input image, I could see, oh, the network failed. So what did the network learn? The network learned to see these sharp discrepancies between the foreground and the background. So then I augmented my data again and I tested it on real images. And okay, I must say it's far from perfect, but the task is also challenging. But we're already happy to have this result. What's next? Next is focusing on the control part, where again, there is actually a big generalization challenge because I can do the control training in simulation, but that doesn't mean that the drone in simulation will act the same way as our real Bebop drone. So I'm seeing some challenges there still, but yeah, nothing we can't cope, I hope. Okay, the second demo is person tracking with adversarial training, and it's also a master thesis student, Cyril van Dalen, that is working on this. Let me give you an update what's done so far. So adversarial trained tracker. The goal is to train a navigation controller that keeps a target in view. I think when you go jogging or mountain bike, you want the drone to follow you. What are the challenges? Well, when you're mountain biking or anything, the target can move in unexpected ways. So if you would just apply a standard a fleeing behavior, let's say, it might not capture all the behaviors required for the tracker. So what is our method? Our method is actually to rely on a competitive self-play. What does it mean? It means that there is a tracking agent and a fleeing agent, and they play the same game, by which one agent needs to maximize and the other agent needs to minimize the same reward. And it's inspired here by the multi-agent autocurriculum game. Okay, I expected the video to play. Let me see if I can play the video. Yes, okay. So what you see here is the blue agents are fleeing, are hiding, and the red agent needs to find them. And by playing multiple games, they get better. Both the fleeing agents get better, and therefore the task for the tracking agent, the searching agents, gets harder. And therefore they create a curriculum in which they gradually both learn. Okay, what have we done so far? So we started with implementing the setting on toy environments that you see here on the right. So where a red square is the fleeing agent and a blue square is a tracking agent, and they're jointly trained in an adversarial way. Yeah, it was interesting to see that this was already an interest in the sense here, if we started off with a reward built on the IOU, namely the intersection over union between the two squares, plus 1 over the distance between the two squares, because we want, if the distance is small, it's good, and if the IOU, if the two boxes overlap, so the intersection over union is big, it's also good. So we put the reward like this for the tracking agent, and then the fleeing agent would minimize this reward. We saw a lot of fluctuations, which you can see here in these large lines in the background. But the adversarial agent could train, given that the fleeing agent did not do anything stupid. If the fleeing agent would stick to a stupid behavior, the tracking agent would only learn to track this specific behavior. If we then looked at the a general reinforcement learning trained agent, a tracking agent, where the fleeing agent was popped up at a random position, the tracking agent couldn't learn at all. But then by scaling the IOU reward and by using a linear reward rather than here an exponential reward, we saw that both the adversarial as the reinforcement, the classic reinforcement learning agent did very well. Actually, the classic reinforcement learning agent here performs better, but that's not a big surprise, because here the classic reinforcement learning agent is trained on an expert fleeing agent. So the fleeing agent is hiding very well, and it's the same agent that is used for evaluation. So because this agent is used both in the adversarial setting and in the reinforcement learning setting, it makes sense that this reward is a little bit bigger than here. But once you don't have an expert fleeing agent heuristically implemented, we expect that adversarial setting is better. Okay, so the next steps is going to drones, step to Ross Gazebo simulator, where they both lift off, and then, well, first they'll probably just fly in one direction and see if they learn to track each other, and then gradually make the task more challenging. And in the second step is going to the real world, where we can use any object detector. So either for following a drone or for following a human, as we give it a certain detector, the control is trained based on the bounding boxes. Oh yeah, maybe to give an ID, because you see the bounding, you get the frame from the tracking drone. It gives only the bounding box of the fleeing drone, obviously, because it can't see itself, but it should overlap with a fixed bounding box in the center. Right. Then the last demo is vision-based autonomous drone racing with our student Thomas Willemot. And so autonomous drone racing has become popular since the challenging 2019 of Alpha Pilot, won by MavLab, I think, maybe a typo. And the goal is to integrate a vision algorithm with aggressive control. So here it's really the speed of the drone that is the focus. And of course, also the real world challenges that comes with flying a real drone. For this, we also work together with the MECOS group from mechanical engineering, where a PhD student has Matthias Bos. He has a racing drone on the one hand and a good controller to control this racing drone. So our task is to apply, provide a vision algorithm on the one hand for detecting cones. The advantage of working with cones is because you can just fly over them and have no risk to bump into something. And then the next step is to do gate detection. From a research point of view, we're going to compare handcrafted methods with machine learning methods. Okay. So basically, what is the input? We have our camera input, and potentially we also use IMU data, and we provide the relative coordinates of the next few cones or gates combined with the orientation. So it's a little bit like we gradually increase the information provided to the control. Okay, what have we done so far, or what has Thomas done so far, is he implemented handcrafted cone detection simply on segmentation, and then estimating the depth on the one hand from the width of the cone, and that's here, width cone 1, width cone 2, and that results in these estimates. But because the racing drone is provided by a tracking camera, it has actually 2 cameras, so we can use triangulation as well, and that gives us a more accurate estimate. So here you can see the detected points for each frame in back to 3D according to the IMU data, according to the global estimated pose. And you see a large spread both in the direction that the camera is going, so in the depth, which is expected, as well as a large spread actually in Z direction, which is because, which is due to the 180 degrees camera. So if the cone is right underneath the camera, it would still detect it, but it's a bad detection. So we should filter that out, but we're still improving. Okay. Then the next steps are switching to a handcrafted gate detection. We have a prototype for this, but it's not reliable. It's not evaluated properly yet. And then also training a neural network and see how well the machine learning methods perform for this, both for gate and detection. This is something we're going to do in simulation, but obviously also want to apply this in the real world. And besides this simulation machine learning track, we expect some further real world optimizations to really improve the speed. Okay, so we can fly through the gates more quickly than this movie.
Hello everyone, I'm Soru Seifi, and in this part of the presentation, I'm going to talk about our progress on the localization part of the OmniDrone project. So the goal of the localization part of this project is to build a map of the environment using a SLAM algorithm, and then to train a neural network like FOSNet to localize any frames within this environment. For any new environment and any new camera, we first need to calibrate our camera. Then we need to have a set of recordings. We feed these recordings to our SLAM algorithm. It produces the ground truth and the map of the environment. Then we can train our neural network on this to localize any frames within the environment. In our previous ISE meetings, we have already shown this whole pipeline on a phone camera and also a fisheye lens. Now in the meantime, we have been trying to extend this to our full 360 camera system. One of the main challenges for the success of this whole pipeline is the correct calibration of the full camera system. Here we have 4 different cameras, so we have to estimate the distortion parameters for each one of these lenses separately. And after that, we also need to have an extrinsic camera calibration where we estimate the positioning of each one of the cameras with respect to the others in the 360 camera system. We did the intrinsic camera calibration with Occam Calib toolbox, which specializes on fisheye and omnidirectional cameras, and we did the extrinsic camera calibration using the Calib toolbox. Then after generating our calibration files, we modified multi-call SLAM algorithm to work with our 360 camera. We also recorded different trajectories, both inside and outside, with different camera movements, so that we could evaluate and understand the SLAM algorithm better. Here you can see an instance of a multi-call SLAM algorithm on one of the trajectories we recorded outside ESAT. So on the left side you can see all of the 4 cameras in our camera system and the features that are being tracked on those cameras. On the right side you can see the map of the environment and also camera movements. I should say that the SLAM algorithm is really sensitive to the extrinsic camera calibration parameters. So by improving on that, we could get even more accurate results. Now I would like to talk more about attention on large inputs, which is part of the research I've been carrying out during my PhD, and it's motivated by the OmniDrone project. In OmniDrone project, we have 4 cameras in our camera system, and each one of these cameras are producing a very large image. This could be problematic for a deep neural network to work fast and in real time. So normally the solution that people would go for is to downscale the image to a size that the neural network is able to process in real time. But the main problem with downscaling is that sometimes you lose some really important information from the image by doing downscaling. So in our research, instead, we try to train a network that is able to select the most important part of the image to attend. So our network would attend some parts of the image, but not all, but it would attend those areas in full resolution. So it can still get benefit from these high details coming from a high resolution image. So as an example, for the image which is on the right side of this slide, there are many regions such as this region or this region or this region that processing all the pixels in those regions wouldn't add much useful information about the environment, and the network can't learn much from those regions. But instead, if the network was able to select some regions, such as those bikes or this tree, or to attend and understand that there is a person here or there is a window here, then it would be able to gather almost all the necessary information from this image. I would skip the architecture details of our network, but instead show you some results from our previous publications on this problem. Here we have a reconstruction problem. This is the full image, the full environment. At the first step, our network attends a random location and tries to predict full reconstruction for the full environment. It also predicts the best next location to attend to gather as much information as possible from the image. So by seeing only these two blocks, it can already say that the upper part of the image is all in blue, and it doesn't need to process all the other pixels in this region. And after 5 steps, and by seeing only these small blocks, it already has a good understanding of the environment and it can reconstruct it accurately. Here are some other results for the reconstruction task and from the same paper. Here are the results for our next paper. In this paper, we try to extend our approach to semantic segmentation problem. So we have an unsupervised training scheme which trains the network to select the best locations to attend to segment all the pixels in the image, including those ones that we haven't seen. For the future, we are planning to improve our accuracy using representation and contrastive learning. We would like to extend our network to be able to predict camera pose. This would be an overlap with the localization part of this project. And finally, we would like our network to work on video streams.